Yeah, I'm recording this session.
Amazing science.
Okay, is my screen visible to everyone? I'll just make it full screen.
Yeah,
Yes,
yeah, we
yes,
can.
it's visible.
Okay, good. Okay, just give me a second. Okay, I think now it is in full screen mode. Let me know in case if it is not in full
No,
screen
it
mode
it
for
is
any
in
of
it
you.
is in full
Okay,
screen
thank
mode.
you. Okay,
Yeah.
thanks for confirming. Okay, so let me start with what exactly we are trying to do here. I spoke with Ganeshan regarding this whole effort around exploiting the capabilities of power architecture and trying to see if we can come out with a kind of an end-to-end solution around power processor, right? Through open development effort is something that we were targeting. And in that context, I know we came together to discuss about some of the key Power 10 features. And I mentioned that the Power 10 implemented the ISA 3.1, and then later when we went back, I spoke to Ganeshan, and we wanted to do things in a more methodological and for logical way, so that we start with the basics of power architecture, give some background on where it started, how it evolved, and also what is the base architecture that we want to understand on Power PC. I know some of you might be already aware of this, but just in order to make things clear for everyone, that when we do a open processor development, we can do it at multiple levels. So we just want to start with the basics of power architecture, ensure that we all understand the foundation here, and then certainly we can pick and choose whatever features we want over that, in order to get what really we want for our requirement. For example, we can take a foundational power architecture, and with a very simple instruction set of, like, say, 100 instructions, and then put your acceleration piece or MMA piece or whatever, right? We want SIMD piece or VSX piece, or and then make sure that we are still complying with the power architecture and go for a chip or a fabrications around that design. And certainly we can go ahead and use it for our own requirements. So that's the kind of objective that we are driving towards. In order to accomplish that, we want to do this as a first webinar, and then completely cover the architecture piece of how it evolved, in what way this is much more well thought and defined architecture, and then go to the next step of, like, getting into each of that areas of SIMDs, MMAs, and stuff like that. And Ganeshan later, he is like planning to bring in more experts from the FPGA team and other teams to see how we can put these pieces together to come out with a real design. That's the kind of input I got from him, and we are doing this webinar to get started around PowerPC architecture. That's a quick introduction. With that introduction, I'm moving on to the first slide. So in today's top agenda, we are planning to cover the architecture introduction, why it is critical, why it has to be defined well thought, even before, like, announcing it, and how it can lay a clear foundation for us to come out with a clear design point. Sometimes we define an architecture and later we think that, okay, maybe this is broken, we need to change this and come out with some fixes in order to get those things done, and all that happens. We have seen that things happening in other architectures in the industry, but from the power point of view, right, it was a well thought architecture that we right from the beginning, it was clearly defined on what the agenda is and how we want to take it forward. So that's something we really want to make sure that we all understand that. And a little bit of history on where this started and how it started and who all collaborated in the past, I would say 2 to 3 decades, around power architecture, and what is the current state of it. And we will discuss few points around the compliance, and what level we can implement this. It is not like we have to do everything when we want to design a power processor. We can start all the way from a very simple processor, and it can go all the way up to a very complicated server class processor as well. And I will try to pick a very basic PowerPC architecture, call out all the important register set and the interrupts and the different type of addressing mode it supports, the memory management, translation methodology, why the translation is very classical in PowerPC, those kind of a basic a foundational piece I will try to cover. And I have like a couple of slides to talk about some of the new features which got introduced in the latest ISA. Doesn't mean that there are many things which got evolved in last few years. And I know when we think about A2I core, it is a power version 2.06. If I understand correctly, that's the ISA version what got implemented, and it is an embedded implementation as well. So certainly understanding this whole topic of power architecture will help us clearly see what processor it is and what features we are putting in and how we can fine tune it to fulfill our requirements for our needs. So that's the agenda what we have got for today. Feel free to stop me anytime in between. We can certainly brainstorm on some of these topics as and when you see some questions. And in case if we are not covering everything today, certainly we will come back and try to do another session to make to cover that up and get it going. Okay, just a quick slide. Really, I don't want to talk about the architecture part for this crowd, but just to make sure I cover this. When we say architecture, we generally refer to instruction set architecture. If you look at the layers of abstraction for a processor design and how the architecture looks like, it's taught all the way from the physics. We talk about devices, transistors, the technology, what we use, the way we define gates and architectures, the registers. Then comes the important piece of microarchitecture, which doesn't have any interaction with the programming aspect of it, but instruction set architecture is actually the mediator here who actually translates the higher level stuff into a lower level thing and make things work. So that is the mode of communication which happens between the programs to the hardware. And ISA plays a very critical role of converting the requirements what we have and sending it to the actual machine and get things done. So that's the role of ISA, and it is very very important for us to understand the nuances around ISAs, which help us define a very optimal and better processor. So it is defined by constituent instructions and their
Yeah,
behavior.
they are. Can I interrupt?
Yes, sure, go ahead.
Yeah, yeah. So what is the difference between machine code and instruction set architecture?
Okay, so okay, it is. I think it is kind of a very mild difference. So sometimes what happens is we can actually generate a certain machine code, but you may not have support, and you can still emulate it, and you can still handle things. It may not be supported directly at ISA level, but still you can manage things. And there are a lot of microcode related stuff which happens and things like that. So machine code at an object level, whatever the object code what we generate with all the linking procedures and all that. So basically it's we don't have to really take it directly, but certainly there is very mild difference which we can call out between the machine code and ISA actually.
Okay.
Yeah, so
Okay.
certainly this can I mean, we can decode it. Doesn't mean that we have to implement everything. So there is a lot of ways we can get it done. So that there is this is anyway a picture which I took from internet, just which I liked it, so that we know that this
Okay.
many layers exist in the architecture, and ISA is the crucial layer where it defines the interaction between the software and the hardware. That's the messaging what really we want to bring out of this slide.
Okay. 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 Okay.
Okay, when it comes to ISA, there are many ISAs out there, and there were like lot more in 1990s, and a lot of things gone out of market, and there are only few which sustained. you can see that even in this list there is only three which are like sustaining, I would say. Remaining things are like uh, sorry, was there a question? Oh, okay, I think, okay, thanks.
That was nice.
Yeah, yeah, sorry, I thought it was a question. Okay, so when it comes to ISA, yes, there are like quite a few ISAs which still exist, and PowerPC, IA32, IA64. Spark has their own ISA, which is right now owned by Sun Microsystem. Wax, ARM. There are many other ISAs, right? Risk and other things, and there were like a lot more in the past. But certainly, the as market matures and or the overall ecosystem evolves, it's not possible both economically as well as like technically to support all the ISAs. Only like a few guys will sustain in the long run. So certainly, yes, PowerPC is clearly known for risk type architecture. IA32, IA64 is known for like say a CISC, and ARM is actually known is a risk, purely risk, but it had its own space of operating in the embedded side, and clearly it is also evolving right now into the server space and making a lot of progress with a new cloud coming up and all that. So certainly there are ups and downs, and different architectures are like trying to venture into different spaces. PowerPC had presence in embedded, automobile, rovers, Mars rovers, and all the different places. It got matured, and it came down to be a very superior server class architecture. IA32 didn't have much presence in the mobile space. It was more like a desktop architecture, but certainly they're making a lot of good like at least engagements in the server side as well. Spark was very, very successful in the beginning, but over the period of time, it kind of narrowed down, and it's moving into a few Oracle specific customer class machines where Spark or like say Oracle supplies, and Sun is anyway no longer exists right now. So Oracle owns it right now, and they are taking it forward for their own specific customers. Yes, a lot of inroads in mobile space, in the IoT and all that space, microcontrollers, and now they are trying to jump into server space with a lot of startups trying this out right now. And yes, and Amazon is also having a cloud which is based on ARM server class processors, which is kind of getting good traction. So there are a lot of things happening in the ISA space. So certainly, none of the architectures other than I think Wax and Spark, I would say, is out of market. But all are like playing their game right now in the market right now. Okay, coming to Power ISA history. So Power ISA actually I would say it's like 50 years old right now. It started as a concept 1970s when Dr. John Cook from IBM introduces the RISC concept. It was kind of taken for granted right now, but during 1970s it was a very an out of box concept where simple instructions was defined with fixed length when it is easy to decode and handle, and none of the operations are like done at direct from memory or anything. All the things has to be brought to the registers in order to handle or do any arithmetic operation. So that actually defines the reduced instruction set, and they were able to come out with a compiler for it, which is pretty simple, and prove it, saying that yes, this is a path that we should take going forward. So that way, IBM designed their first RISC design, IBM 801 in 1980s, and that followed by RS6000 series, which we can call it as the first IBM power processor. And there is a certainly a lot of things happened during 1990s. That's the time where ISA race was happening, I would say, across multiple people. Alpha was there. There are many things, many competitive ISAs were there. So at that time, IBM, Apple, and Motorola came together and formed an alliance called AIM. And that is where they defined the architecture called PowerPC, which is a direct derivative of this RS6000 class architecture. So when this was designed, it was Motorola did their own processor, Apple was using it for their MacBooks, and IBM was using it for designing their server class processor. And it continued that thing for a longer period of time, and it made inroads into rovers, it made inroads into gaming consoles like Xbox, PS3, and many architectures all across the board. I would say all the way from simple automobile requirement and all the way up to like space rovers, right? Power processor had its presence in different form. And based on the market it captured and how it evolved, later the power.org was formed in 2004 timeline. And then actually it evolved since 2004 in various different ways. And right now we are in 2020 doing our power 10 server plus process, and a lot of other things happening in parallel as well as part of the open power community effort. Taking it little forward, when the Power 1 was released, it was the first of the Power class processor. We had like around 218 instructions, and it was a very simple RISC design, but it was pretty successful. And Power was actually like was a forefronter in terms of implementation as well. When it comes down to like multi-core implementation or SMT implementation, this was actually done I mean, first in Power, I would say. I mean, just before any other processor or architecture made it. And those are the classical things which has happened. And if you see right now where we are, right, at Power ISA 3.1. So all the way from Power 1, it evolved in different forms. So 1990s, the Power PC Alliance was formed, AIM Alliance, and then a lot of embedded processors got developed, and server class processors were developed. So 1997, we saw a need for creating a separate version of Power ISA, which is specifically targeted for embedded. There was something called PPCE, which evolved. And there were two chain, or at least like two threads of ISA, which was evolving in parallel. And during the 2006 timeline, this got actually merged into one version, where 2.03 was the first version, where the power server side and embedded side got merged into a single definition. And but still we were maintaining a separate a category for calling out the embedded features. And after like 2.07, it got into a single version, not calling out embedded separately, but it is more like a single version of Power architecture, which is 3.0. And right now we are at 3.1. At different stages, the Power architecture evolved with different type of innovations. Like say SIMD was the initial one, which Apple used heavily in their initial versions of Mac. That VMX was the feature which was extensively used there. And then we got the VSX part. And right now we have the on-chip accelerations like MMAs and prefix instruction support to take our architecture to the next generation. So it's a quick timeline view of from where we started and how Power evolved as of today. Okay, now I'm going to cover around the compliance, right? Because this is important. Now, as I mentioned, right, the Power ISA has a single view of say Power ISA V3.1, which has like 1,400 odd instructions, right? To be precise, 1,419 instructions. But it is not possible for everyone to implement a full Power ISA and be full architecture compliance. So certainly there should be different levels of compliance that we should allow. And as part of Open Power ISA, there are like at least 5 levels of compliance that are like approved, and it is in place with a very simple implementation, starting with a scalar fixed point subsets, which has only 129 instructions. And we can add floating point to that to make it 214 instructions, and that becomes like SFFS. And then comes the Linux subset, which takes you to a 962 instruction kind of ISA support. And then the AIX subset with 1,099 instructions, and the full ISA compliance comes with 1,419 instructions. This is at instruction level that we have like different categories and different levels of compliance that we can support. But doesn't mean that you are limited by 129 instructions alone. Suppose if you are going in for an implementation at scalar fixed point subset, which has 129 instruction, you are allowed to add optional features over that. And that can come from any of these subsets, which are called out as optional features. And also there are like certain features which are like purely optional, right? It's not falling into any of these categories also. So I'll show that in this slide. So here is a better view of how the compliance works. The base architecture is the scalar fixed point subset, SFS, with 129 instructions. Then comes FP, scalar FP, and that is scalar fixed point and floating point subset. And then the Linux subset adds SIMD to it. And it also adds LPAR, logical partitioning feature. It adds like nested radix translation support, and then the 64-bit mode and OV yeah, and then few other cases as well. And then comes the AX subset, which adds support for decimal floating point, quad precision, big endian, branch history buffer stuff. And there are many more things to call out. I don't think we can go into details of each of this right now, unless otherwise it is important. But certainly, based on interest, we can go into each of this topic if that is of interest for this crowd in the later stage. And there are like optional features like MMA, secure memory facility, which is going to provide a container level security mechanism, data stream prefetch, power management capabilities, and a lot of non-coherent memory capabilities and all that stuff, which are purely optional. And this can be brought in into any of this level, and then we can implement that as well and still make sure that this is Power ISA compliant. So that those are the kind of compliancy subsets what Power ISA offers at this moment. And what we are planning to do is start here, right? The base architecture. We just want to go into a little bit more details about the instruction set, the type of implementation or ISA definition we had for fixed point, floating point, interrupts, and all that stuff. And we can come back on any of the topic which is of interest for the crowd to cover floating point separately if needed, and also MMA, SIMDs, secure memory facility, whatever is of interest. And this is at ISA level. We are not getting into the implementation of it. So the implementation can be done out of order or superscalar, whatever way we feels. And there is one like implementation already open sourced, which is the A2I core, and that is certainly 2.06 compliant, and it has a lot of features. So implementation is left open, and we can go with our own implementation with our own cache sizes, our own branch predictors, and all that stuff. It's pretty much open. And from the ISA standpoint, this is what we have right now as a up to date information on the Power ISA side. Any quick questions before we jump into the base architecture of Power ISA?
So you said that 100% compliance is not done.
No, it's not required for all the implementation is what I'm saying. So this is certainly done at our own implementation at like different Power 10 has a 100% compliant for 3.1.
Right.
What I'm saying is like when others from the open community or like when external people want to implement it, they really don't have to do everything. They can pick which level they want to get compliance, and then they can pick up appropriate sets and they can go ahead and do their own processor implementation is what I was trying to say. So they can start as simple as this SFS, right? So that
No,
way just get 129 instructions and still it is a Power architecture ecosystem support set, the tool chain support set, the compiler supports it, and we know, right, this will work out of box. So that's what we that's what
so
I meant when I say compliance at
okay.
different levels.
Like I want to say, um, I want a server class processor. Requirement is HPC. For that, you need the full,
Yeah, I would say
right?
we can go for this Linux option, this level with 962
Mm.
instruction, which covers most of it, and that will get you like say all the SIMDs, all the translations, everything, and then we can add the optional features like MMA. I don't know whether you are really need secure memory facilities and all that stuff, which can be left out. And we can pick the Linux subset and then put MMA to it, and then we'll get a good server class HPC processor, which does most of the stuff what we want. I don't think there is like much needed on this side. Decimal floating point is all not needed. So really, I think decimal floating point was done for a specific reason, for a banking requirement, and it is used by a very limited set of customers, I would say. So really, we really don't want a full compliance there for doing a HPC type processor implementation, right? DFP, I don't think will be of much interest for you. And
Mm.
SMT, to large extent, I would say, from the ISA standpoint, there are certain features we offer, and we can do SMT implementation. There is no problem with that. But at ISA level, we do offer some SMT features, which is not of, I don't know whether it's of very significant value add for HPC side. And yeah, the branch history buffers, the event-based branch tracking, we have like ISA support for those kind of things as well. I don't know whether those things are really required. So certainly, I think at Linux subset level will be good enough, and we can bring in like features like MMA, optional features, and make it a very server class HPC processor for the requirement what you have. That will fulfill all the requirements. I think we can go a little more detail, but that at that very high level, that will be more than enough for getting a HPC type
Okay.
processor.
Before move on, one last question, if you don't mind.
Sure.
Like the floating point, suppose my requirement is I need double precision, single precision,
Yes.
and B float, even integer 8-bit operation, all these things are required when I'm designing the HPC processor.
Yes.
So, at what level this will satisfy that?
Yes, so this SIMD supports double precision, single precision, and also a non-IEEE class VMX feature as well, which will be a fast arithmetic, but it will be like non-IEEE compliant. So that will cover that. MMA supports all the lower precision operation at this moment, and all the integer 8-bit operations. The classical instruction supports that, and for getting whatever requirement, I mean, whatever requirements you have, I would say Linux subset plus pulling in a few optional features like
Okay,
MMA, and then
MMA.
we
Okay,
can pull in quad precision. This can also be done along with this. This is actually an optional thing as well, and we
okay.
can still make it work. We can what we are trying to say is, like, if you really want to design a processor, you don't have to worry about all the features that
Yeah.
has to go in, but certainly there are ways we can do sandboxes, and then we can pick and choose the
Yes, yes.
required architecture, and we have clearly defined it, right? What can be optional, what is mandatory. So that way, we have to fulfill the mandatory requirements, and we can pull in whatever optional features are available. So these are always optional, but doesn't mean that these are the only optional features. There are optional features that are available within this subset as well. The AX subset also has optional features which can be pulled in into the Linux subset. So that's what I meant when I
Okay,
say optional within each subset. And there are always optional features which are like outside of this subset, so which is what is listed here.
okay. Thank you.
Sure. Okay, so now in order to understand the architecture, right, in whatever I called out was so far the way we organized it and the compliance part and all that stuff. So this whole architecture has been split into three levels, environments, I would say, to make things simple, so that different people can pick up different sections or environment and they can work on it. So for example, book one is basically all non-privileged user instruction architecture. So that will be purely used by compilers for code generation purpose, application level programming, direct assembly programming. It actually covers all the user level instructions and all that stuff. So there is no like nothing to deal with memory management or what operating system has to worry about or what hypervisor has to worry about. And it is all like purely user level, right? So this is what application level programming model. So if you are a compiler developer or if you are an application developer who are interested in library development at assembly level and all that stuff, what you need to know is just book one. You really don't have to bother about book two and book three, which goes into other areas, right? So that way, this gives you a complete control over how you want to program your application at assembly level, and also how you want to write your compiler in order to generate the best code for the particular architecture. Book two is like a very small book, but still it has a lot of value. It deals with the cache management features, like flushing of caches and prefetching of caches, and some level of storage features, and time and synchronization related events, which I would say it's non-privileged for certain requirements, and it is also like it covers time bases and all that. So it's a kind of virtual environment architecture, we call it, and it defines the storage model for threads and resource interactions and all that stuff. So it is not a very heavily used thing, and it is also not very huge. It is a limited set, which is not, doesn't fall completely under book one and not goes into book three. So we kept it as book two. And book three is where all the supervisor or privilege level things are being handled. And that means like all the exceptions, interrupts, the way we do translation, the way we deal with page table, segment table, and all the stuff around whether it is hash page table or radix page table, everything comes under book three, which is what the OS developers or firmware developers and hypervisor developers need to know. Without this, they cannot really write the memory management features of Linux. And this is all explained within book three's boundary. So all the debug facilities, special resources, special purpose registers, everything is covered under book three. So when we go to the next few slides, I will give you a glance of, from the base architecture point of view, what all registers are called out as book one, I mean, covered under book one, and what all registers you will be accessing in book three, and how that is being handled by setting the appropriate mode in the machine state registers, like whether you're executing in the user level, or whether you're executing in the privilege level, or whether you're executing the hypervisor level. So that's something which is clearly defined right from the base architecture, I would say. It is not like we worked this out in between and try to come out with a kind of a workaround to handle this. It was clearly defined how LPAS has to be created, what registers are used to create LPAS, and it's actually embedded in the fundamental design. So we have independent registers for handling LPAS to keep the LPAR IDs and all that stuff. So overall, I think that's the reason I said like it was a clearly thought out architecture from the beginning, because a lot of experience and learnings came from the Z architecture as well, which was one of the classical architecture which had virtualization and all the capabilities, right? 20, 30 years back, I would say. There was no software workarounds to do it like VMware's, and it was all handled in the hardware. And we have like all the support in the hardware or ISA level to handle it in a very precise way. So that way, Power had a lot of inputs from RISC, from Z, and it had its own uniqueness, and all put together, the Power architecture has been evolved over past years. Now, so though I said that it had a history like starting from 1970s, the formal official Power PC class processor came out during 1990s, and almost like it is 30 years old right now, where we have our current Power 10 announced this year and will be coming out in the market next year. That's the latest processor which supports the latest ISA 3.1. Okay, now I'm getting into the base PowerPC architecture. Okay, so this slide is little overloaded, but it is still worth just glancing through this once, because this lays the foundation for our Power architecture, right? What defines what features we have in Power architecture, the base architecture level. So it is certainly a risk. We all know that, and it is a register file-based architecture. I would say there is nothing like you can do addition of two memory address or anything. It is all handled at register level. So there are like 32 initially when PowerPC was defined, 32 GPRs and 32 FPRs was defined. So for GPRs for primarily handling fixed point arithmetic, and FPRs was primarily defined to handle floating point arithmetic. And then instructions for loading and storing data to these registers. So it is a clearly defined one where any arithmetic has to happen in register, and data has to be brought into register to do that arithmetic, and then it can be moved back. So it is a load store architecture. So you do a load and do arithmetic and store it back. So that's how the foundation was laid, and all the instructions are of uniform length. We are maintaining it till now. Even though we are allowing prefix extension in 3.1, it is also a fixed length, 64-bit right now. Earlier it was 32-bit, and starting from 3.1, we are extending it to 64-bit, and we will have the reason why we are doing it is to allow more innovation to happen and more instructions to come in and handle things in a much more efficient way. So it is a uniform length instruction set architecture. It doesn't have like 1 byte, 2 byte, 4 byte instructions kind of thing, but it's uniform length, all 32-bit instructions. And non-destructive use of registers is very critical, because when the reason why 32 registers were defined is for operating and keeping the registers. Sometimes you see, right, you have to use the same register as a source and target, but that is not something we envisioned. We really want to keep most of the registers non-destructive, and so that we can, even for instructions like FMAT kind of thing, right, we keep most of the things non-destructive and try to play around with it. So typically the initial thought, right, these all defined in 1990s, I would say, right. So that way this was clearly thought out at that time. A very precise exception model, right, with options of treating floating point exceptions imprecisely. So the exception model was defined very precisely. For each and every exception, there was a clearly defined address where will jump to, and we will handle the interrupts. And OS has no problem to implement this, and it is very, very easy to understand. And we will just see, right, what all interrupts we support and how we handle it. Right from the beginning, it had support for IEEE 754, or both single precision and double precision, and it fully compliant with IEEE. And later we also had extensions which is non-IEEE compliant, which is what the VMX was, and that was a requirement which came through the Alliance, and Apple wanted for their like initial versions of Mac. The graphics was like was a big requirement at that time, and it was like very well covered by VMX architecture, which was, I would say, like initially we had that thing as a SIMD architecture to bring it to the market. And then there are a lot of other things, the ability to perform single and double precision floating point operations, user level instructions for explicitly handling caches, which is also defined in the initial architecture. How do we bring data to the cache? How do we flesh out the cache? And a lot of these things has to be done as part of operating system features as well, because sometimes we have to flesh out the cache, sometimes we have to prefetch the data into the cache and all that stuff. So there are instructions like cache block touch instruction, cache block zeroing instructions, and then flushing instructions called DCBF and things like that. So it is all part of the base architecture. And memory model, which is again very important one, and also the translation part of it, which is also very important one. One of the unique thing which I would like to call out is, initially when power architecture was defined, it came out with a single page table for the entire system, right? So when you think about page table, you generally think about one page table for each process. So that is not the case in power. You can have a single page table which handles all the processes in the system, right? So that's a very classical and also a well thought memory model. I mean, I would say memory management, and that way it was one of it was a classical architecture, and it's quite interesting to understand that if you are an operating system developer, you will be really attracted towards that design. And support for instruction and data caches right from the beginning of the design, support for both big and little endian, and support for 64-bit addressing. So these are the classical things which got defined in the beginning of power architecture in 1990s timeline. And then from there on, it extended and started offering more features around LPARs, more features around SIMDs, and more features around, like right now we have MMAs and prefix architecture, and a lot of extensions in terms of like both fixed point and floating point arithmetic as well. So that's how the base foundation for PowerPC architecture was laid, and from there we went into the evolution of the power architecture. So let me jump into some more details around this. Right, I talked about some of these things at a very high level. Let me try to touch base on each of this topic quickly and give you a quick overview of what this is about. Architecture models. Okay, any questions so far before we jump into the next section of the presentation?
Is the number of registers, sorry, the number of registers you said 32 and 32.
Right.
Um, is that fixed even with the latest 3.1?
No, that's the base architecture. So I'll talk maybe a little bit on that. So initially the floating point was scalar, and we had like 32 FPRs and 32 GPRs. So right now we want to support vector. So we extended the 32 FPRs to 64, but still the classical floating point unit can use only 32 FPRs. The VSX extension, which we have brought in as part of the SIMD architecture, can use all 64 floating point registers. And we also extended the size of the floating point registers from 64 to 128. So right now, if you look at it, we have 64 128-bit floating point registers, which can do SIMD operation. That is where we are right
Okay.
now. And that is also
Okay.
same set of registers are used by MMA as well. So there's no new register which we have defined separately for MMA. That makes programming also pretty easy and straightforward to handle. So that's where we are. So GPRs, it's still 64-bit and 32 GPRs. There is no change in GPR side.
Okay.
Yeah, and
Thank
that
you.
is doesn't mean that. One more thing I just want to add. That doesn't mean that since I said fixed point arithmetic is handled by GPRs, you may get a question, right? Then can't I do like SIMD operation on a fixed point, or I'd say integer operation? Yes, it is allowed in as part of VSX extension. We do support integer. And what actually happened in terms of implementation right now is like we kind of unified the register file internally. And that means like you can easily move values between GPRs and FPRs seamlessly, as if like you are accessing one set of register file. It's not internally, it is not like a two different register file. Physical registers are sitting as one register file. Architecturally, you will be seeing GPRs doing fixed point, FPRs, and I'd say VSRs, right? Vector scalar registers doing both fixed point and floating point SIMD operation. That is where we are right now. So you do have support for vectorization and SIMD support for both integer as well as floating point arithmetic. Okay, so yeah, so jumping into the architecture models, we want to understand these things, right? Registers and programming model, operand conventions, instruction set and addressing modes, cache model, exception model, memory management model. These are the foundational piece of PowerPC architecture, and that is being covered under 3 levels: and user instruction set architecture, virtual environment architecture, and operating environment architecture. As I mentioned earlier, UISA is like book 1, VEA is book 2, and OEA is book 3. So book 1 is more about compilers and assembly programming. VEA is more like cache management, time base, and synchronization kind of stuff. And operating environment architecture is more about OS, hypervisor, and all that thing. So LPARs, all that stuff is covered under OSA, including translation and the segment tables, page tables, everything falls under operating environment architecture. So all of this thing, architecture models, will be covered in one of this section. And to just give you a glance of how simple the register set is in terms of UISA, I called out earlier that we had like 32 GPRs, we had 32 FPRs, And whatever operation you do on these things has to be captured in terms of exceptions, in terms of like supporting registers, which are very simple, right? Condition register is one. We have over and above this GPRs and FPRs. We have floating point status control register, which is FPSCR, and we have XCR, and we have link registers and count registers. I will just tell you what exactly the different purpose, I mean, where we use these things. And these are the base registers all you have in the power ISA or power instruction under the user model. So it's very simple. So you can easily name it GPR, FPR, LR, CTR, XCR, and LR. Yeah, that's it. So that's I mean, so CR and FPSCR comes in the next slide. So those are the simple registers, and I will say what exactly it does. So the condition registers are used for various purpose. So condition register captures the the result or the status of a fixed point arithmetic operation. Okay, so when you do an add or subtract or anything, right, you may overflow, you may like run into a zero results, and you may, when you do a compare operation, it may be an equal or I mean greater or less than. All of those status is captured in the CR. So you can program CR by providing one as a output and do a compare of two values, or you can do an add I operation with dot. So there is a dot to add I, and that will actually automatically captures the result or status, not the output result, but that the status of that operation, and that comes to CR. So why it is so simple and effective is like beyond this point, in order to control the control flow in your program, you can just check the CR bit. All the branch instruction operates by looking at the CR bit and make a call whether it has to take the branch or skip the branch, right? Whether it's a taken branch or a non-taken branch can be done by looking at CR. So CR has access to the branch unit, and branch can easily, seamlessly flow by just looking into one of the bits in each of this, any of this register. So we have 8 CRs, each of 4-bit, and each bit is like used for, like, one is for 0, one is for greater than, one is for less than, and I think one is for overflow. So there are like 4 bits. I can share the document and you can easily understand that. So now coming down to floating point status control register, this captures the status of the floating point operation. Whether you are raising an exception, you're running into a zero divide case, or like whatever the exception you are running into. Um, and also it defines the rounding mode for your floating point arithmetic. So there is an interesting piece to it. You can still do a branch based on the result of a floating point operation. So what happens is you can actually copy few bits, exception bits from FPSCR to CR as well. This copy happens automatically for a lot of floating point instructions. So that way there is no need for any external management. Automatically the status is being captured in FPSCR, and some of the status can also be transferred to CR as well. So that way FPSCR is the key register in order to understand what happened as part of your floating point operation. So each bit has its own purpose, and then like you can say zero, overflow, underflow, rounding mode. FR stands for rounding mode, and like divide by infinity, not a number, whatever, right? So divide by zero. For each and every thing, what happens for floating point operation, that is clearly captured in the floating point status control register. So any mission critical applications, or any of the banking or trading application which needs a high level of precision, right? Which can be handled very simply with the availability of all these registers. Okay, so those are the key registers. I'll just talk about link registers and count register, which serves for multiple purpose. So link register is actually used for function calls and returns, and count register is used for loops, where you want to loop through a function. You can just put some count into the count register and let the branch loop, and the branch will continue till the count registers become 0, and once it hits 0, it will automatically exit the loop. So there are like instructions which supports that kind of branches, called BD and Z, branch decrement, count registers, and continue. And also these are used for function jumps. So you have to put in a value into the link registers in order to jump to a function and return from the function and all that. So from that point of view, yes, these are the critical things. And the XCR also has a exception, fixed point exception register. So any exception which happens in the fixed point side is captured as part of XCR. So I think that covers most of the arithmetic operation. And with like 7, 8 registers, right, set of registers, you are kind of having a complete control over your program and see what's going on and how that has to be handled. And most of these things are like people at application level, they don't bother because it is being handled by compilers and compiler do the job for you. But when you do a low level optimization, which generally people do in the embedded side and like floating point library side, right? They do develop a lot of assembly codes. It is very simple for them to get the code return and understand when they look into it. So that's the beauty of the simplicity of the architecture what we have here. Okay, now I'm going into a little bit more details on the operating environment architecture, which is called supervisor, or I would say privilege level architecture. And this has a very important register called MSR, which stands for Machine State Register. So certainly understanding this is very important because this defines what state the machine is in right now, whether it is in user mode, whether it is in privilege mode, what kind of things it supports in terms of like whether it supports floating point or not. You can disable floating point, you can enable floating point, and you can do a lot of things. And you can say you are running in LPAR mode or you are running in a hypervisor mode. All that status of what the current state of the machine is actually sitting in the MSR. And MSR is a privilege mode register, and that cannot be touched by user level instructions or anything. And certainly this is the I would say the key controller of the machine of power architecture. PVR is a very simple register which is read only, which tells you which version of processor you're running. So it's a processor version register. And coming to memory management, there are few registers which we added at a later stage, but the base is like SDR1, which gives you the address for the page, the base address of the page table. And then we have like registers like ASR, DAR, and DASR. All like these things are supporting registers. When you take an exception and go into the interrupt, you need to take certain values from the user level to the operating system level, right? In order to handle the interrupt, understand which address you need, you for which you have got a like a page table exception or anything, translation exception, and how do you handle it, right? So those kind of things are actually handled, captured using these exception handling registers called DASR, save and restore registers called SRR0, SRR1. So SRR0 gives you for what address you missed the translation, or you got a page table exception, or say a data exception, right? And then SRR1 captures the state of the machine during which the exception occurred, so that when you come back to user mode, you can restore the state and you can continue execution. So these all are like clearly defined registers. There's nothing which changed significantly to handle things now in a different way, but certainly there are a lot of extensions as well. So all of these things I would say is like still like valid, and it is doing its job. And over and above this, there are like new registers like LPCR, logical partitioning control register, LPIDs, and all the partition IDs, and all those things are tracked using a new set of registers introduced when we introduced LPAR into the power context. And there are miscellaneous registers like time base, decrementers, and other stuff, and which helps you like with decrementary interrupts and looking at time base for handle or synchronization purpose and all that stuff, right? So those are some of the miscellaneous registers what is supported in OEA. So if you understand this picture, I think beyond this, it is just an extension. So when you read about 3.1 ISA or 2.6 ISA, it will be very easy for you to map it to the base architecture and see what got changed and what is the new feature or new extension we got in the different versions. Sometimes people get lost when they look at these big books, and they don't get that flow of where to start and what to look for and all that stuff. So these things help you with a clear picture of what is user mode, what kind of registers we do, we operate on, and what is OEA, that is book 3 operating environment mode, and what kind of registers we operate on. So that's a quick overview of operating environment architecture register set. So here, this is the view of MSR, as I said, right? Whether it's 64-bit or 32-bit, because Power ISA supports both. We can set that SF bit says that. PR bit says what privilege mode you are in, whether it's you're running in user mode or whether you're running in um, privilege mode. ILE says, LE is like Little Endian, and there are like few more things like FP bit. If it is set, it will support floating point execution. If it is set to 0, then you will get interrupt. Even your architecture has floating point, so you can control a lot of things. IR says instruction. I think, yeah, I think the translation part is also covered. And yeah, the description for this is given in book 4, so we can go into each of the details and try to get some more details around that. That's the view of MSR. So yeah. So getting into the memory management register, I think I talked about STR1 already, which holds the base address of the page table, and it also has the size and all that stuff. So I'll just come back to this when I quickly give you an overview of translation part of Power Architecture at the later part of the slide. Okay, coming to the exception handling registers, these are SRR zeros, SRR ones, data address registers, software SPRs G0 to 3, which are used as a scratch registers for operating system to move, keep some of the things right without spoiling the user status before saving the context. You need something to like operate on, because everything is done through registers, right? You need to provide some kind of buffer space for interrupt code to operate, and for which SPRs are heavily used. Data storage, interrupt status registers, and floating point exception cost registers are additional registers used by operating system to understand like the segment interrupts and all that stuff, right? Which address the segmentable interrupts occurred and all that thing. In terms of endianness, PowerPC supports both Big Endian and Little Endian, and now there is a kind of a fully compliant support for Little Endian. Earlier, in the initial version of PowerPC, right, it was a Big Endian processor, but it had like limited support for Little Endian, I would say. And the MSR bit LE and ILE actually indicates whether you are running in a Little Endian mode or Big Endian mode, right? So that's the MSR status bit. And if that is set, then the processor will operate in Little Endian mode, and if it is not set, then it will operate in Big Endian mode. So that's a single bit control to make your processor run in any Endianness you want. And in the recent time, we migrated to Little Endian, and a lot of the current Linux, the open, the all the newer versions of Linux operating system and all that stuff runs in Little Endian, and AX is still running in Big Endian mode. So that's where we are. Initially, we were running in Big Endian for Linux as well, but right now we migrated to Little Endian. So the default mode, I would say, for open ecosystem is more like Little Endian mode right now. Okay. Um, Coming to operand alignments, yes, natural alignment boundary is the operand length, because we do support different types of loads and stores and operations, right? It's 4-bit loads, 8-bit, 16-bit, half word, double word, all the different types of loads and stores are supported. Generally, the natural alignment is operand length, and most of the non-aligned cases we do support, but doesn't mean that everything we support, right? Some of the misaligned cases may cause exception, and that is clearly defined in architecture. You don't have to really bother about it, and that can be fine-tuned. Like if you really want to support non-aligned cases and all that, yes, it is allowed, and most of the things are quite handled well. But in terms of performance penalties, you may run into performance penalties when you do the implementation of non-aligned memory operand access and all that stuff. So that's the operand alignment part. And coming down to instruction set and addressing mode, we do have different type of instruction forms. We do have different addressing modes, and then the instructions are grouped based on different functionalities, right? The arithmetic, the compare instructions, then branch instructions, and there are different groups of instructions, which we have clearly defined so that it is easy for us to understand how many groups exist and what kind of operation we do in each of the group. So in terms of instruction length, as I said, it is all 4 byte. That means it's all 32-bit fixed length instructions. And recently we extended this to 8 byte support, using prefix architecture. So that means going forward, the PowerPC architecture will also support 8 byte instruction word. And the execution is program order, and like instructions are clearly called out, whether it's a user level instruction or a operating privilege level instructions. And effective address calculations are based on done for both 32-bit and 64-bit based on the MSR SF bit. If it is set, then it is a 64-bit arithmetic, same instruction. If it is not set, then it is a 32-bit stuff for the same instruction. That is pretty easy to switch between 32 and 64 here. In terms of different type of instructions, PowerPC offers you integer instructions, floating point instructions, load stores, branch and flow control instructions, processor control instructions, memory control instructions, synchronization instructions, and external control instruction. I'll give you some quick examples of what kind of instructions you do see in that other categories like memory, synchronization, process, and external. I'll show some examples. Integer instructions are straightforward. It is like simple arithmetics all the way from add, subtract, multiply, divides, mod instructions, and there are a lot of extension to it, right? At a Boolean instructions, bit level operations, maskings, and all that stuff. Everything, whatever you can think of it, actually, right now with the full architecture compliance, we do support it. And the base architecture supports all the foundational instructions what are required. Floating point, to call out, right, the floating point is always a tougher field to implement. It is not so easy to get a good latency and good implementation. So classically, if you look at the 1990s architecture, floating point started with the multiply add support, all the way from the beginning of its architecture, right? So the floating point, fadd, f subtract, f mul, f divide, f square roots, and multiple fm adds, right? It's called multiply adds. Floating point multiply adds was supported right from the beginning. A lot of the other architectures actually adapted that multiply add kind of instructions very recently, I would say. Even if you look at x86, right? Only with AVX2, they brought in the multiply add support. Prior to that, the multiply add instruction was not there in x86 architecture. So, this was like, it was defined right from the beginning, and it's a very well thought, clear implementation of floating point, both 32-bit sync scalar and double precision, right? Single precision and double precision are very well thought of implementation. And internally, the way we represent the values and the way we make sure that IEEE compliance are achieved is very, very clearly defined, and it is very simple. And there's nothing like 80-bit representations and all exist here. It is, if you look through the programming, both either the ISA or the programming environmental manual of Power ISA, you can clearly see how the scalar operations are handled. And I have a complete set of slides which covers the floating point unit alone, which both scalar as well as vector, which can be dealt separately. But I just want to give a quick view of what it is, right? So that way, it's a well clearly defined floating point implementation, I would say, instruction wise as well as compliance wise. Load store instructions, it's also like, as it's a load store architecture, it supports different addressing modes and all that, and it is also well defined. Branch and flow control instructions are like both, if you look at it again, right, it has supports for both direction flow control as well as indirect. That means jumping to target address, you can put in target address, you can jump to it. And there is also a conditional indirect where you can check for a condition and jump to a target address. And if you look at it, all these are like defined in the base architecture. Again, to call out lot of the competitive architectures like x86, right? They don't have a kind of a compare and a jump to a target kind of instructions exist right now. It is internally handled in many ways based on microarchitecture, workarounds and all that stuff, but still those kind of architectures are very easy for us to do the programming, and compiler code generation was not existing in the past and even now in the x86 side. So yeah, so those are the things that we just need to, I'm just calling out few things which are different so that people can understand the importance or significance of that. And coming to processor control, memory control, we'll go through these things in the future slide. Coming to addressing modes, load store instruction supports three type of addressing mode. We recently added support for PC relative addressing as well. So you can do PC relative loads and stuff with the current version of ISA, which supports PC relative addressing. So the classic addressing modes are like register indirect with immediate index, and register indirect with index mode. So register indirect is like you don't have any direct address. The address sits in the register and you have to take the value from the register and jump to that address, or like load from that address or store to that address. And the register indirect with immediate comes with a base register and an immediate value. So the immediate value gets added to the base register and you jump to the target. Oh, sorry, you load from the target. You cannot do direct jumps on GPRs, just for your information on PowerPC. So I have to correct that statement of jumping. Okay, so it's a mostly load store handling here. Register indirect with index mode is like direct indirect address. And another two registers are there. One holds the base register and the other one is an index register, and you add those two things and you can load and store to that particular address. So those are the three type of addressing mode which are supported in the Power ISA. From the branch instruction standpoint, you can do three type of jumps. You can give some immediate address as part of instruction. You can jump to that address. And this got extended recently so that you can give much bigger address and you can jump to it directly. And also PC relative jumps are right now allowed. Link register indirect is like you put the target address into the link register, jump to that address. So that means this is basically used for like function calls and returns and all that. Count register indirect, you put some target address into the count register and you can jump to that address. So those are the ways in which the branch instructions operate, both for conditional and indirect side. So that's the addressing mode part of Power ISA. In terms of memory synchronization instruction, these are the foundational instructions, right? These are used for lock handling, and it is heavily used in parallel programming and all that stuff. And it's also used by operating system to maintain all the semaphores and all that stuffs, right? So locks and stocks are the instructions which are used to maintain the synchronization, right, across instruction, right? So that's something which is also clearly defined. Locks is for word level handling, and LDARX is for double word level handling. And these instructions actually internally set some bit, and when someone tries to modify it, it gets reset. So you have to kind of loop through it in order to take the lock, do the kind of the operations, the synchronization operation, and then you can continue the execution. So these are lock stocks case for memory synchronization. Context synchronization instructions are like sync and RFI and RFID, which are like basically return from interrupt, and SC stands for system call, and isync is instruction sync, and MSR is like move to MSR. So whenever you do change of state, you have to do a context synchronization, and whenever you return from interrupt, you have to do a context synchronization, and when you do a system call, you have to do a context synchronization. And isync is a separate instruction which allows you to do the context synchronization as per your requirement. A lot of times when you handle page tables and flushings and all that stuff, right, you end up doing context synchronization. Execution synchronization is done for by sync instruction, as well as when you execute empty MSR, it also does execution level synchronization. Coming to instruction forms, as I said, the PowerPC instructions are like 32-bit. The first 6-bit defines what opcode it is, and the remaining bits are used for like mentioning the registers, input registers, output registers, what kind of operations you want to do, and all that stuff. And there are like wide variety of instruction forms available: I form, B form. I'm not going to go into details of this. This can be understood by looking through book 1 and what kind of instruction forms we support. And in terms of exceptions, exception causes a change of state from the user mode to the privilege mode. And exceptions are handled in program order. All of the exceptions are handled in operating environment architecture level. And multiple exception conditions can map to a single exception vector, and they can be handled in the program order, obviously. So those kind of supports are added as part of the ISA. And exceptions are actually classified into asynchronous and synchronous. Asynchronous are system cost exceptions, and synchronous are instruction cost exceptions. So you may get exceptions coming in externally, right, through IO and all that stuff. So those are like asynchronous, and synchronous things are caused by instructions when you try to do a load and it misses the translation table, and you have to go to the operating system to install a page table entry and or a segment table entry for that, and come back and continue the stuff. So those kind of synchronous exception can also happen. So we support both. And like, yeah, and also there are like precise exceptions and imprecise exceptions when it comes to synchronous. And we have like floating point imprecise mode exceptions, and some are recoverable, some are non-recoverable as well. So this is like to accelerate things and move things faster. I think I can skip this slide. I kind of covered it. And the way the exception handling happens in Power ISA is like the moment you get an exception, the the okay the processor will trigger an exception and it will jump to the exception vector. So when it jumps to the I'll show like what vector it jumps to. And the different registers like SRR0 will get loaded with the address of the instruction, so that you can return back to the same place when you are returning from the instruction interrupt handler. And SRR0 is loaded with the specific information of MSR in which the processor is operating right now. For example, whether it's running in 32-bit or 64-bit, whether FP is enabled or disabled. So those kind of things, right? MSR bits, the key bits are actually captured in SRR1. So these are like these registers are automatically loaded. Then you jump to, you set the privilege bit automatically on when you get an exception, and you go to the exception handling code, handle the exception, and you can return back using RFID instruction, right? So that way, it can be 64-bit or 32-bit, and you can just return to the address what is stored in SRR0. So that way, the exception handling is pretty straightforward. And you can see that for the different type of exceptions, there is like clearly defined addresses for which the processor will directly take a jump. For reset, it jumps to 100. For machine check, it jumps to 200. Data memory access interrupt, this is page table miss, and then jumps to 300. Segment table miss, it jumps to 380. And the instruction table, instruction address error, it jumps to 400. Segments to 480, and all that stuff, right? So I'm not going to the details of this. For FP unavailable exception, it jumps into 800. So sometimes if the floating point architecture is not implemented, and if you want to execute something, you can still run the code and you can emulate it by using the interrupt handler as well. So there are like quite a few things that can be done. We tried out few things for different requirements, and we use in exception handler in a different ways, right? When we do internally some of the works to validate processors and stuff like that. So yes, it's quite interesting, and it's important that we understand some of these things, even though we don't like run into these things on day-to-day activities. It is always good thing for us to know some of these basics that helps us get more confidence in the ISA and architecture level. Exception priorities, yes, always non-maskable asynchronous instruction takes priority, which is system reset and machine check. Then comes the precise synchronous instruction, then comes the imprecise one, and then the maskable synchronous one. You can mask decrementers and external interrupts so that it never uh, triggers any exception in the processor for a certain period of time. That is possible when you handle the when you deal with by setting appropriate bits in MSRs, right? We can certainly do that. Just one page on address translation. I mean, I think I brought up this point some time back when I was talking about translation. I said like Power Architecture supports a single page table for the entire processes or processes running in the system, which is like when I read about it, it was like quite new for me in the very beginning of my career, because I got used to like multiple page table for each, I mean, each one page table for each process kind of stuff. So it was little difficult for me to understand this and grasp the concept behind it, but certainly it was interesting, and it is quite unique as well. So the way it is operating is you have the 64-bit effective address, and it is clearly defined like the first 36 bits are effective segment IDs, and it gets into the segment table, and the remaining bits are like page index and byte offset within the page index. So you may, okay, later we extended the page size support from 4 KB to like 16 KB support, 64 KB, 4 MB, 16 MB, and 1 TB as well, right? So we have a very wide variety of page supports right now, but initially the base architecture support 16-bit page index, and then say um, offset of page of byte offset, right? So that's what we had initially, and then this gets translated using segment table into a virtual segment ID, and that is an 80-bit virtual address. So this is little different if you compare against x86 architecture. We generally use the terminologies in a different way. Virtual address is being used in different forms in different when you deal with different type of domains. So here it is basically an internal address. This is the address which goes to the page table, and page table helps you translate this virtual address into a physical address. So there is a quite a bit of algorithm which are associated with this. I'm not going into the details of that unless we have a need for that, which certainly we can cover in case if any of you feels that there is something that we want to cover in that space. But at this moment, I'm keeping at a very high level. So there is an effective address which goes to segment table, and you get a virtual address which goes to the page table, and you get a physical address. So what I mean is this page table is actually common for all the process, right? You have independent segment table for each process, and you have one common page table for all the process. So that's how the page translation or address translation works in the Power architecture. Okay, so I am right now on the last slide, I would say, which talks about a quick summary of Power ISA 3.1. I know I'll not be able to cover the details of this, though we have called out in the, at least in the abstract, that we will go into some details of 3.1. We can come back to this and we can cover these things in little more detail. In the new version of ISA, we actually introduced two major things. I just want to call that out and then go into some of the minor things that we introduced. So one of the biggest thing what got introduced is the matrix math assist. I think we spoke about it in little detail in the past session around Power 10, but we have not gone into the details of how the operation works and what kind of math we can do, and how like the internally the things are like working, right? Just from the architecture point of view, we have not covered the complete details around MMA. So that is certainly the reduced precision support and outer product operation support for Power architecture, right? Built on chip. So that's one thing which is major. And the prefix support, which is like moving from after 30 years of evolution, right? Moving from a fixed 32-bit instruction word to a 64-bit instruction word support is a very big move. And this is basically done to allow future extension for our ISA. And that is another major thing which happened. Apart from that, the lot of support, vector integer operations got added. We added support for 128-bit binary integer operations. There is like support for bit manipulation operations, permute class instructions, mask operations, and also 32-byte loads and stores. When I say 32-byte, it's 32-byte, not 32-bit. So it's a big load and big stores can be done on multiple VSRs. So that way we are really reducing the number of instructions that is required in order to do a loads and stores, and that's very important for doing like HPC type computation as well. So 32-byte load store support is added. And in terms of other operating system level and other translation management extensions and hypervisor interrupt localization control, some extensions to persistent storage or store sync instructions, and also extensions to branch history loading buffer and some of the newly performance monitoring facility, sampling, and all that stuff. These are PMUs are used for monitoring the performance, and that is also part of ISA. So those kind of debug facilities or also extensions have happened in those areas as well. And I think that's the very high level view of what got extended in ISA 3.1. And we will spend some more time later on some of these interesting topics, right, around matrix, math assist, and other stuff in a separate presentation, along with maybe the floating point, general floating point architecture. The VSX and matrix math assist can be clubbed together, and we can dive into the details of floating point as a separate topic that can be done. So I think that's most of it, what I have for today. I hope this gives a very quick overview and also a good flow on how to look at Power ISA and how to read it and how to understand some of the features and capabilities what we offer. I will not be able to, I mean, I would say like 1 hour is not enough time to do justice to explain all the architecture capabilities, but I tried my best to at least give you a good a source of like how the architecture looks like and what are the important features that we have to keep in mind when we go back and read the ISA. So that's what I tried to do. I hope it is useful, and we will come back on more interesting topics in other sessions. I'll stop here, and we can go in for a few questions before we close for today.
Yeah, Satish, thank you very much for your detailed and detailed presentation. Thank you, sir. I think panelists. I think there are a lot of people are here. Mr. Kumar.
Yeah, I have been asking questions in between.
Yeah, I know. Thank you, thank
And
you, thank you
and
for.
I must say Satish has covered it very excellently, and it's a nice presentation, giving
Yeah,
a overview of everything. Yeah, as he said, we would be interested in those extensions, particularly that this matrix math assist and all those things,
sure.
SIMD and other things. As he said, we may have another session later on
Yeah.
after we discuss among ourselves.
Yes, sir. That is a plan we have actually.
Yeah.
So definitely the MMA and other features will help everyone, to understand the features of Power 10 and and the upcoming processors.
Yes.
Any other questions from the team? I
Hari,
know. I think I muted him because he has
Yeah,
been.
yeah, yeah.
Okay.
he's
Yeah,
been creating noise, is it?
yeah. So one question is quick question, sir.
Uh,
Is it what is the reason behind selecting only three addressing modes? Memory, indirect, only three of them out of all other addressing modes. Is there any proof?
Okay, so actually we felt that is okay. I think that's we felt like we were able to cover most of it, and that gives a comprehensive coverage to handle most of the load store instructions. But if you think there is a need which is being left out, which can be fulfilled by other addressing modes, I think there is it's not a big deal. But I think from my point of view, we were able to cover most of it. And I said, right, recently we added PC relative addressing mode as well, so that way you can do relative loads and relative stores with respect to your current program counter values. That means the IAR's instruction address, and yes, that can be done with the current ISA. So we now have like 4 different addressing modes for loads and stores, and also that is applicable for the PC relative is applicable for branches as well. So that's no specific reason, but we felt like this is more than enough. And I don't know, maybe as I said, right, I was I was not there in 1990s, but this there was beyond that, we didn't see any requirement which popped up in order to add more addressing modes or anything. So we really didn't bother to make any extension to that. Uh,
Understood. And one more informative thing. Most of the performance related, it depends on how do you actually implement your microcode, right? The instruction.
Microarchitecture, yes, that is right, and that is the reason I clearly called out in the beginning of the presentation, right? So the ISA is actually the layer which bridges the software and the hardware, and you can go in for any type of implementation for this ISA, and it can be like a completely in order, because we did in order implementation, which is one example is Power 6 processor was an in order processor. We can do out of order, we can do a scalar, super scalar. We can put in a very simple branch prediction and go for it, or we can put in more complicated branch prediction and do. It's up to us to decide how you want to go about the implementation of the processor. There is no restriction to that, and that's what exactly AMD and Intel is doing right now, right? They both support x86, and they do have a different implementation internally, though in a lot of sense, right, they do have common implementation as well. But if you look at it from outside, right, it is same thing runs on both sides, same code, but your performance will be different. The way, and it is a very important thing, right? Microarchitecture defines your differentiate, that provides the differentiation, right? ISA is more about ecosystem functionality, compliance, and compiler compatibility and all that, but implementation is where the real difference comes in. Yes.
Thank you very much, and it's a nice presentation.
Thank you, Satish, and thank you, Mr. Hari. Any other questions from the panelists, attendees, participants?
Nope.
Sir, excuse me, sir.
Yeah, Venkatesh, go ahead, please.
Sir, hi, sir. This is Venkatesh.
Yeah,
This was a
Venkatesh.
very informative session, sir, regarding the Power ISA and also Power PC. Um, Thanks for giving this valuable information. And also, I would request to have a session regarding the Power 10 floating point unit, VSX, matrix math assist. If possible by next week, it would be very helpful for us.
Okay, yes. So there are two aspects to it. Again, I think Dr. Hari brought it up, I guess. So there are two aspects. One is ISA, and other one is like implementation, right? So both for VSX, floating point, and MMA, Power 10 has a certain type of implementation, but doesn't mean that we have to do the same implementation if you go in for a different processor, right? If you want to do our own processor, we can certainly do it in a different way. So what we can do is we can split it. ISA part we will certainly cover from FPU, I mean floating point, VSX, VMX, and MMA. These are the key things what we have in Power ISA, and then we can cover the implementation part of MMA in P10. I think that way it will be a good mix, and we will try to see if we can do it next week. I'll talk to Ganeshan on that, and if time permits, we will certainly get it done before we go on vacation this year. And I'll talk to Ganeshan on that and see if we can cover that topic next week.
Yeah, sir,
Thank you.
sure, sir.
Thank you.
Actually,
Yeah.
we are actually using this open sources. We are planning to develop an fabless SoC, Anand
Hmm.
1.0 at our college, sir. Um, Purely, this is indigenously developed for R&D purposes. If want, I can show a small view about the architecture also, if time permits. And the panelist, will request the panelist.
Yeah, I'm fine with it. I'll let Ganeshan and others make a call on that.
Yeah, sir, Mr. Kumar and the CDEC team, is it okay for Venkatesh to showcase 1 minute about his, the whole group plan?
Yeah, sure.
Okay, please go ahead, Venkatesh.
Yeah, sir. Thank you, sir. 1 minute, sir. So this is a fabless SOC architecture, sir.
Mhm.
Using all these peripherals, we are planning to develop a fabless SOC.
Mhm.
These this power core will act as the main processor. In this, we have an L1 memory, and here we have an L2 memory, and also here memory control these flash. These flash memories will act as an L3 memory, sir.
Mhm.
And we are using these peripherals like Ethernet, SPI, I2C, and PCIe. I would request any suggestions for this. Any if
Now,
if
what
possible.
is the target application class for this?
So
Is it,
actually,
are you targeting embedded systems?
so we are planning to implement in an FPGA, sir.
No. Once you have the core fabless SOC, is it like you're going to close there, or you're going to offer this SOC for some class of applications?
So for R&D purposes, sir, it's purely for.
Okay, it's for your own interest.
Yeah, sir. Yeah, sir.
Okay. Then the overall architecture, if you leave PCI Express, PCI,
Yeah, sir.
it appears for an embedded class of applications. Then
Yes, sir.
actually, I don't know why
That is
PCI is
right.
required in this architecture. That you may require for your application.
Okay, so we will look into it, sir.
Because generally, the all other bus interfaces, including DMA, is most widely used in embedded applications.
Yeah, sir.
And PCI, I have not come across any such use case of PCI in embedded, particularly. So if you are targeting multiple classes of applications, that is fine.
Yeah, sir. Yeah, sir. Thank you, sir. Thank you so much for your valuable suggestions, sir.
When you say R&D purposes, are you going to use this in a lab for trying out the various things, or?
Yeah, sir. We are trying out the various things. Means the versions will continue, sir. Like presently, we are working on 1.0 version, sir, 1.0,
Mhm.
and later on, the coming batches may use implement some other versions.
So
Extend upon
yeah,
that.
No,
let
that is right. But like Hari said, if this this is tied up with the target application, then its purpose is solved. No.
So we will look into it, sir.
Yeah, see here, originally, one of the leader here, who assisted to develop this, he is not available today due to some emergency. But
Mhm.
definitely, there are things, which he has in his idea too. It is part of his PhD. That's the reason,
Okay.
he actually initiated this with
Okay.
the JNTU. And also this is going to be specifically like kind of a platform for future students who can use that actually kind of R&D.
Yeah, that's what I
Yeah,
understood. I understood.
yeah, we even the Columbia University has got ESP platform like that, multiple universities building a platform for them to integrate
Mhm.
more things in future, and
Okay.
as part of that. Yep.
Yeah, that way
So,
it's a good
yeah,
initiative.
now I understand.
Yeah, Satish, you
So,
want to add anything in this?
Venkatesh,
Uh,
where are you from actually?
So I'm from Andhra Pradesh, sir. JNTU College,
JNTU. Okay.
Anantapur.
Anantapur Jayanti. Okay.
Yeah, sir.
okay. Yeah. So you are basically planning to get an FPGA, right, out of this. So that means you will be able to run the real codes and get something working, right? Not purely only simulation or anything, right? So you are targeting to get FPGA implementation of this.
Yeah, sir.
Okay.
So do you have the boards that has enough logic cells
Yeah, that's what
to
I was
accommodate
thinking.
this SOC architecture?
No,
Uh,
I'm actually going to support that actually,
okay.
going
Then it's
forward
fine. Then it's
as
fine.
we go. Yeah.
So it is IBM funding.
I'm not saying IBM funding. It's
Mm.
basically through
Ganeshan fund.
open power ecosystem.
Okay.
I can say open power ecosystem. I have a lot of open power partners,
Okay.
who are making it available actually for people to use it and all. So I'm going to use one of
Which
those.
FPGA is being used? Tar-
Now it's Xilinx only,
Now,
sir. Xilinx
yeah,
has
sir.
got
Xilinx,
a lot of variety.
Xilinx. Yeah, sir.
Xilinx.
Because Altera has been bought by Intel. I
Mm.
don't think so. The availability of Altera FPGAs as
Mm.
free as earlier. And
Mm.
now Xilinx also is in talks with AMD, I think.
No, no, I
So
think deal is
that deal
done.
is done. The deal is
Done.
done. It's
Deal
part
is
of
done.
yeah.
Actually, people are consolidating.
Yes.
The HPC industry, processor industry, they are consolidating.
Yeah, so
Yeah.
one big thing which is happening in the industry is like if you really look at like say Amazon, Graviton kind of stuff, they are going for like ARM, and ARM deal is also done mostly with
Yes, yes.
NVIDIA. So the point is like the domain specific type of stuff with the homegrown SoC is really getting a lot of traction
Mm.
in the market, and Google is also looking for, I guess, some kind of their own like SoC or a chip, right? Based on either ARM or any other architecture to build their own cloud, because this seems to be like doing pretty good as well, Amazon's Graviton. So yes, I think there's a lot of traction in the industry right now around this field, and it's certainly maturing. It was kind of considered like only certain group of people or companies can do this, but now it is becoming more like a software type of evolution where anyone can take it and then they can go for it and do a fabless and even get fabricated right through various different companies. So it's a good thing, and at least from India point of view, we are at the very it's the right time for us to jump start here and keep things moving in this space. That way I think we'll be able to keep up to the industry momentum here. So that's a good thing what I'm seeing, and it's really, I'm happy to see that happening across the world as well. So that's really make things much more interesting.
Okay.
That's true.
Yes, Satish.
And
Sure.
towards that, the IBM's initiative of open power architecture also is a good move. Like where it's a kind of their own architecture where they can build their processor or SoC around it without much implications towards licensing. That's a good move actually.
Yeah, and also the heterogeneous and multi-purpose the ISAs from the open source world,
Yeah.
that is also going to be a growth area. Certainly, next 5 years you're going to see the momentum joining open power and RISC-V kind of a platform, SoC architecture and all, like may grow too. So I do see that. I'm hearing lots of universities in US and Europe looking at that, building something jointly, with RISC-V and the open power course as a kind of a SoC. I mean, a multi-purpose, the heterogeneous kind of architecture. Even
Oh,
Venkatesh putting together some architecture on that too, with his
okay.
own personal interest.
Oh, that's good. That's
Yeah,
good.
I
Yeah.
can see. Yeah, AXI4 in between. Okay. See, Ganeshan,
Yep. Yes, sir.
uh, all it is fine, but when are you enabling us to build a processor?
Yes, sir. Let's talk, later on, in our call. And this is a webinar. There are people still attending, and we will call that in a separate meeting, sir.
Okay,
We'll
sure.
have a meeting.
Sure,
And
sure.
yeah, Professor Mamta, you have any things to add here from JNTU, and Professor Ravichandra from SRIT? Do you want to add any things from SRIT, sir?
Yeah, sir. Good evening, sir. Suppose people, our students want to work maybe in this particular area. So, what is the role of our students if they want to work really?
Yeah, that I wanted always, all your students, to be part of the meeting so we can work on a plan. So we will have a separate meeting, sir, with your
Okay.
students.
Okay, sir. Okay. Thank you.
Sure. And Mamta, madam, you wanted to say something?
Yeah, nothing much. But here I have seen a lot of people from CDAC and IBM. One thing, even afternoon also, I have seen that few students came to me and asked like they are stuck at coding, like a way to start, how to start. So here a lot of people are there, so they may help how to start, like whatever protocols they have taken. So Arjun is giving lot of inputs to them, but Arjun also busy, right? So if you provide coding part, like how to start, like way to see, way to get the knowledge. If you provide the Ganeshan, students can take those inputs and they will
Yeah,
like develop
yeah,
protocols.
yeah. I'm working with Venkatesh on that. Actually, certainly, there will be some webinar,
Yeah.
on that angle. Actually, that's a
Okay.
separate webinar, madam. I will do that. Not a
Yeah.
big deal.
Okay.
Sure.
Okay. Yeah. That's it. Good.
Thank you, madam.
Yeah. Okay.
Any other questions? Okay, I think we are almost like 1 hour 44 minutes we spent on this webinar. Thanks for that. Thanks for the CDAC team, Mighty team, IBM, all the the Sastra, JNTU, and SRIT, and also many more people in the webinar who joined initially and now um, still staying here. Thanks a lot for all the support, and let's see. Let us see. Hopefully, have another webinar next week or next year. Thanks a lot, team, for attending the
Thank you,
webinar.
Ganesh. Thank you.
Thank you.
Thank you. Bye.
Bye.
Thanks
Thanks,
everyone.
Satish.
Bye bye. Thank you, Ganeshan.
Thank you,
Bye bye.
Satish.
Yeah, bye.